Okay, hello everyone. Welcome to 130B Quantum Mechanics. So let's start our lecture today. Last time we have already covered a lot of things in harmonic oscillator, but maybe let me briefly go through this summary again to remind you what we have learned. So for harmonic oscillator, it's a very simple one-dimensional quantum mechanical system. It describes a particle in a quadratic potential. So the key observable there is position and momentum. But in order to solve this problem, we basically perform a transformation, which we recombine position and momentum into annihilation and creation operators, such that they inherit a certain non-trivial commutation relation of position and momentum. And by defining the number operator, we are able to eventually find that this number operator has a discrete spectrum. Its eigenvalues are all natural numbers, and there's corresponding eigenstates. Not only that, we also know how to apply annihilation and creation operator on these number eigenstates, and then the annihilation operator annihilates the particle, creation creates the particle, but there is an additional square root factor in the front. Given this expression, we can also see that if annihilation operator acting on the zero state, which is the zero particle or ground state of the system, this square root of 0 will directly go to 0, right? So even if 0 minus 1, like this minus 1 state is not defined, but because the coefficient in the front actually goes to 0, so that doesn't cause a problem. So by definition, if you annihilate a particle on the zero particle state, there's nothing to annihilate, then this algebra just refuses to give you any finite answer and returns a 0 in the end. Okay, so that's the definition of the ground state. So you can treat this as a definition in the sense that you can say ground state is whatever state in the Hilbert space, such that annihilation operator acting on the ground state or acting on the zero particle state gives you 0. So we need to distinguish the zero particle state and the 0. 0 really is a zero vector whose norm is 0. But zero state is a state labeled by n equals 0. It's still a finite state. It's still a unit norm vector. Okay, so that's the difference. Okay, with those understanding, we basically rewrite the harmonic oscillator Hamiltonian in this form, and then we can find its eigenenergies or the eigenstates. And interestingly, if once we define what is the ground state, what is the zero state, we can use that and our knowledge about creation operator to create particle on the vacuum state, and then that leads to all the n particle states or the nth energy level for harmonic oscillators. And towards the end of the last lecture, we further discussed the representation theory, which means that how do we represent all these abstract algebraic relations in terms of matrices. In order to do that, we need to first represent every state as vectors. And then the simplest way is to consider them as one hot vector embedding. And then with that one hot encoding of vectors, we can write down matrix elements by simply taking this inner product. And that gives you for example, the mth row, nth column matrix element. From that, we know A and A dagger looks like that. Given that, we can further construct the number operator, which fits our intuition. It indeed gives us all the eigenvalues arranged on the diagonal, which is what we should expect, because we are basically representing all the operator in the number operator eigenbasis. Any Hermitian operator represented in its own eigenbasis will be a diagonal matrix with real eigenvalues on the diagonal. And what is more interesting is that we can further represent position and momentum operator in this both on number basis, and then they look like that. And based on that, one can further check that indeed the position and momentum operator satisfy the commutation relation as we expected from the very beginning. So this just say that sometimes, regardless how you represent this operator, their algebraic relationship is absolute, and then it's representation independent or basis independent. So today we are going to make more connection to position and momentum, because when we solve this problem, we introduce annihilation creation operator. But in reality, when we try to observe a harmonic oscillator, we are still observing its position and momentum. So what can we say about these physical observables in the system? One thing that I want to talk about is the uncertainty relation. Uncertainty relation states that the standard deviation of x and standard deviation of p multiplied together must be greater or equal than the absolute value of x and p commutator evaluated on the state on which you evaluate this standard deviation, okay? So because x and p are observable operator, in this case, their commutation relation is I times identity matrix, and no matter which state you evaluate this operator, it's always number I, basically, and the absolute value of that I basically is 1, so in the end, it just say that the standard deviation of x and standard deviation of p must be greater or equal than 1/2. Of course, I have already set a Planck constant h bar to 1 such that the commutation relation looks like that. If you append this Planck constant, then there will be a h bar here and there will be a h bar there. Okay, so let's stick to this convention and then let's try to check. Is it really true that, for example, for this harmonic oscillator, we have many energy eigenstates, or the so-called Fock state, or the boson number eigenstate, this state n? So we can arbitrarily pick one state and try to check whether the standard deviation of x and p indeed satisfy the uncertainty relation. In order to do that, we first define the position and momentum operator. Again, rewrite it in terms of creation annihilation operator, because that's how we can apply them on this number eigenstate. In order to calculate the standard deviation, the first thing we need to do is to compute the variance. Maybe you still remember that the variance is given by the difference between x squared expectation value minus actually x expectation value squared. So there are two things we want to compute on a given state n. That first thing is what's the first order of x, what's the expectation value of x itself, and then what's the expectation value of x squared. We can show that the expectation of x is 0. The reason is that if you substitute this definition here, you will do either this n-particle state will be annihilated by one particle or created by one particle. Of course, this process gives you some prefactor which has this square root form, but what is more important is once you annihilate a particle on the n-particle state, that becomes a -1 particle state. And that state is orthogonal to the n-particle state because they are eigenstates of different eigenvalues of a Hermitian operator and guaranteed to be orthogonal. And the same argument applies to this n+1 because when you apply a dagger to n, then to create one particle. So no matter you annihilate or create, you are not ending up with the same state of the same particle number, so that automatically become orthogonal to the original n state, and then these two terms, these scalar products vanishes. So regardless of what factors in the front, the answer is 0. Okay, and this is actually a very very reasonable result because for harmonic oscillator, it has the reflection symmetry, meaning that when we write down the Hamiltonian, in the Hamiltonian, p and x all comes like a p squared plus x squared, right? So if you change x to -x, the Hamiltonian doesn't change. So if the Hamiltonian has a symmetry where you flip the direction of the x-axis and then nothing gets changed, then all the eigenstate of the Hamiltonian will preserve this symmetry, and then this eigenstate, you can see, indeed preserve the symmetry, meaning that this x expectation value should not take any finite value. If this x expectation value dare to be any finite number, any non-zero number, I can immediately perform the symmetry transformation. X goes to -x. I will get a different answer. But then these two answers are related by the symmetry. They should be the same. So that proves that this expectation value must be 0. Okay. And then we can also compute, that is more important, we can compute x squared. I want to tell you how to do that. Although we don't have the wave function now, but we can still use creation annihilation operator algebra to complete this task. So here we have a dagger plus a dagger squared. And then that expands into 4 different terms. There are this term which annihilates the boson twice. Then that term basically vanishes because you start from an n-particle state, annihilate twice, n goes to -2, and that's going to be orthogonal to n. And this creation twice also goes to 0 for the same reason. But there are 2 intermediate terms, which is this cross term when you expand this square that goes like a dagger and a dagger a. You annihilate one particle and create one particle, or first create and then annihilate. These can lead to non-trivial results. So for the second term, you can see this A dagger A is nothing but a number operator, so that directly gives you a number n. But for this first term, we need to use the commutation relation to commute A dagger through A, and the answer is A dagger A plus 1, so that goes to n plus 1. And then basically summarizing all the results together, you get n plus 1/2. So this basically shows that the variance, well, the variance is defined to be the standard deviation squared, that is the variance, which is given by x squared expectation value minus x expectation value squared, which equals n plus 1/2. And we can perform the similar calculation for p squared. You can see in this problem, p really has no difference with x. They are basically on equal footing. So the answer is still n plus 1/2. But now we want to take the square root of these two, because these two lines are variance. They are not standard deviation. Standard deviation is the square root of the variance. But now if you multiply the square root together, you recover this n plus 1/2 again. So given that n is a positive integer, that this result never gets smaller than 1/2. It's greater or equal than 1/2. So indeed, that's what we previously derived from the uncertainty relation, as you can see here. So this proves that for any energy eigenstate of the harmonic oscillator, this uncertainty relation is indeed satisfied. But given this result, you can also see that when n equals 0, a very special case happens. That means this inequality becomes an equality if and only if this n particle number is 0. So only in the ground state that it's a state that saturates the uncertainty relation. We say that the ground state is a minimum uncertainty state. The fact that the ground state still has a finite amount of 0-point energy actually has to do with this uncertainty relation. The argument is as follows. So because of the uncertainty relation, now I'm squaring the uncertainty relation. Instead of talking about the standard deviation, I'm talking about the variance, basically, given the knowledge that the expectation value of both x and p are 0. So the variance is directly given by the expectation value of x squared and p squared. So if the standard deviation product is greater or equal than 1/2, then the variance product must be greater or equal than 1/4. And given that, you can show that if I want to evaluate the expectation value of my Hermitian, here the expectation value of my Hermitian is not only at the energy eigenstate. You can evaluate, you can create any state. You can create superposition of energy eigenstate, which is no longer eigenstate of Hermitian. Doesn't matter, you can still evaluate this thing. So that means no matter what state you choose in the Hilbert space and try to evaluate the Hermitian expectation value, which correspond to the energy, then it will goes like p squared plus x squared in this way. But then given that x squared times p squared is greater or equal than 1/4, then you can replace this equation by inequality, which means this thing, no matter how large it is, must be greater or equal than p squared plus 1/4 times p squared. And this expression, if you try to draw a picture, let me try to draw a picture here. So I want to draw the horizontal axis is p squared, and the vertical axis is p squared plus 1/4 times p squared. So this p squared means that there's a straight line. And then 1/4 times p squared, meaning that there is like an inverse this relation, right? So if you plot them together, if you connect them together, that's the result basically. If you add the two curves together, there will be a minimum somewhere. And then the minimum, you can show that if you do a little bit more algebra, the minimum is at 1 p squared equals 1/2, and the minimum value is 1 here. Is 1. So that means no matter how I parameterize this curve, no matter what's my p squared value, this curve never gets below 1. So that's why I can replace the whole curve regardless of the value of p squared by this prefactor. And then that basically proves that the 0-point energy must be, there must be some energy in the system. Even if you try to go to the ground state, even if it is the lowest energy state, cannot be lower in terms of energy, lower than h bar omega over 2. This is because there's a competition between the fluctuation of x and the fluctuation of p. So if you are trying to make this fluctuation of x very small, that means you are measuring the position very accurately, meaning that you have an accurate knowledge of the position, so you can reduce this term. Then you must be very uncertain about p. Then the p can go very large. The momentum can be very, very large. That creates a lot of kinetic energy. That's not good. But if you try to make the momentum very small, that means you are trying to reduce the uncertainty of momentum, then you create uncertainty in position. So there's this balance between momentum and position, and eventually the ground state is the minimum energy state, which has the least amount of fluctuation in both position and momentum, but still there is an unremovable fluctuation there, and that corresponds to the 0-point energy or the minimum energy, or the uncertainty relation basically gives this. Okay, so this applies to a single harmonic oscillator, but we know that in our universe, all the particles are actually coming from oscillation of fields. So basically, we have many this kind of harmonic oscillator. For example, every photon in our world is a boson that corresponds to exciting certain harmonic oscillating mode. So even if you are in a vacuum state where there's no matter, no photon, no light, there is still this ground state energy associated with the existing mode in our universe, in the quantum field theory, actually. So these invisible energy, actually, it becomes the dark energy in our universe, which takes 75% of the energy content of our universe that comes from this kind of 0-point motion of the quantum field theory. But really, if you try to compute what should be, based on this principle, compute what should be the dark energy, you will find that actually that's what in cosmology, people find that the dark energy will be several orders of magnitude much larger than what we observe nowadays. So that strongly hints that there are some particles we haven't observed or we don't know yet that contributes to the dark energy, and then that cancels the dark energy in some sense. So here I was talking about these bosons. Boson has actually a positive 0-point energy. But what I didn't talk about is for fermions. Fermions like quarks and leptons, like electrons, is a fermion. So for these fermion modes, their ground state energy or their 0-point energy is actually negative. So if the boson energy and fermion energy can somehow balance, that will explain the dark energy problem in our universe. And then people believe that maybe there's a solution to that, which is called the supersymmetry, which means that there are same amount of boson and fermion in our universe. But maybe that's too far from our lecture. But this is just, I want to say that even just in this simple harmonic oscillator, we can see some very fundamental facts about quantum mechanics. This uncertainty relation actually requires that even if the system has no motion, it has some amount of energy associated with quantum fluctuations. Okay. So here comes the homework 2. The homework 2 was designed to give you an opportunity to exercise the way to compute, for example, physical observables. Because what we want to understand is actually, for example, x, what's the expectation value of position and momentum, and maybe what's the expectation value of x to the 4th power, right? Because suppose I want to evaluate what's the expectation value of a function of x on the ground state, right? Maybe I have that kind of that's the most general observable, at least in terms of position. You can evaluate something like that. But previously, if you try to evaluate that, basically you take this function and then take the wave function, right, psi 0 of x, and then squared, and then dx. You just do this integration. But now, in our approach, we never obtained this ground state wave function yet. So we don't know what's the wave function. And how do we evaluate this function, this expectation value in its very general form? The idea is that this, anyway, is a Taylor expansion of all powers of x. So as long as we can evaluate something like x operator to the mth power, and you can actually show that x operator to any odd power will have expectation value 0. And only x, that is because of the symmetry that I just mentioned. There's a reflection symmetry that guarantees that all the odd power position operator will have a 0 expectation value, but the even power will have a non-trivial expectation value. So this homework is trying to give you an opportunity to figure out this expression, basically. So with this expression, you can substitute that into Taylor expansion series and compute any function of x without doing any integration on the ground state, at least, okay? So the way to do that is actually following what we have in the lecture notes about how to compute this x square, right? If you know how to compute x square, I think you should be able to come up with a method to compute x to the fourth power. And then you eventually need to use mathematical induction that suppose x to the 2m power looks like that. And then can I further generalize that to x to the 2m plus 2 power, right? Then if you can do that, then probably you can prove these statements, okay? So that's the homework 2. Any questions? Mm-hmm.
Could we also just maybe start off with the mathematical induction proof and then use that to solve for x to the 4th?
Yes. You're challenging yourself, but yes. Yeah, originally the design was x to the 4th. By doing that, you will realize there's some rule, there's some trick, or there's some regularity, and then using that. But if you can directly prove it, it's also great, yeah.
And then just a follow-up question on that, which is if we're looking at an inductive proof, looking at our base case, I presume that would be like x, would that be x squared then?
Yeah.
Because are we assuming the natural numbers are non-negative or positive?
Even m equals 0 is fine. So here, I know you will raise this question. So the definition, I need to explain this double factorial. Double factorial means that you take a number and then, for example, double factorial of 3 is actually 3 times 1. And double factorial of 5 is 5 times 3 times 1. It's like every time you, instead of decrease by 1, decrease by 2, and then multiply them together. So it's like factorial, but it's of every time decrease by 2. So that's what we mean by double factorial. But if now you take m equals 0, it's by definition that there's a definition, double factorial of minus 1 is actually 1. But apart from this very singular case, so that case, then actually that's okay. That's a base case because that's like identity operator has a expectation value 1. But if you take m equals 1, this double factorial will be 1 basically, and then this basically becomes 1/2, I think. So that also match the base case, I think, yeah. Okay. Yeah, having said that, we can do a lot of things even without knowing the wave function, but still I'm very uncomfortable with this kind of approach. So let me tell you about what the wave function is. Even if we start from an approach which doesn't involve any wave function, in the end, we can still back out the wave function from what we have learned. So the very important equation in order to restore the wave function is this equation. That is the annihilation operator acting on the 0 particle states, which cannot further annihilate the bosons, so it basically gives you a 0. So that means there's some state which correspond to the ground state or the vacuum state, that if you apply this annihilation operator, which looks like that, it goes to 0, which means x plus ip acting on that state is 0. But now, suppose we can represent everything in terms of the position eigenbasis, which means that we are going to represent this ground state as a wave function, because in the coordinate space, in the position eigenbasis, every state is basically represented as a superposition of the position eigenstate by the superposition coefficient, which correspond to the wave function. And in that case, when you apply the x operator on the wave function, that simply multiply the wave function by x. When you apply the p operator on the wave function, that simply take a partial derivative of the wave function with respect to the coordinate and with some factor minus I in the front. So if you substitute all these into this equation, the state becomes the wave function, x becomes a number multiplying the wave function, and then p becomes a derivative operator acting on the wave function. So the whole equation gets translated into this differential equation. this differential equation is the only differential equation we want to solve in this lecture, and then the solution is like that. I think this differential equation is not very difficult to solve. You can try it by, if you don't know, you can click this open and then try to solve it. So the answer basically is the Gaussian. If you don't believe it, you can substitute this Gaussian into this equation, and then you can show that it's satisfied the differential equation. So it's a solution of that. And it turns out to be the only solution of that, as long as you normalize the state. Okay, so this basically gives us the ground state wave function, which looks like a peak, a very broad peak. Not very broad, but, but the standard deviation is actually unit. Okay, you can also do a first excited state. How do we do that? Now you can just apply the creation operator on the ground state. Once we know the ground state wave function, applying the creation operator is simply taking this operator, which corresponds to how x and p combines in the creation operator, right? So, but applying this operator simply means you take this wave function, take derivative of x, which can be done, and then also multiply the function by x, which can also be done, and put them together, and that's your answer. So following this approach, we can basically start from the wave function of the ground state and recursively construct all the excited state wave function all the way out of the ground state. So that's the power of this creation operator. You just create n times, then you go to the nth excited state. So there is a general expression for the nth excited state of harmonic oscillator, I think, which was what we learned previously. But when we learned that, I was very terrified by the Hermit polynomial. I can't memorize all this. But now we have a unified principle. We just need to know how to find the ground state by solving that very simple differential equation. Then all the excited state is nothing but just related to the ground state by keep applying the creation operator. So you can really write a computer program to do that. And then this is actually a program that I wrote. And then it gives you a table. Like for the ground state, it looks like that. And then for the first excited state, there's some expression, but that expression is related to, it always takes the form of a Gaussian and some prefactor, which is very tedious, and the Hermit polynomial. Hermit polynomial basically increases in terms of order as you go to higher excited state. For example, this is a zero-order polynomial, first order, second order, third order polynomial, and so on. So Hermit polynomial is just a sequence of polynomials somehow given by this creation operator, generated by the creation operator. Keep applying that, and then that gives you all the wave functions. Okay, so that's what we learned previously. I think these pictures are familiar to you, maybe. So that's what I want to talk about the harmonic oscillator. So in this lecture, we took a very algebraic approach. We didn't solve differential equation until the very end, but already this algebraic approach can provide a lot of information about the system. It allows us to evaluate all kinds of expectation value. That's actually what we need. Wave function is not what we need. Wave function is just, if you plot it, it looks nice, it looks beautiful, but it doesn't, eventually you still need to compute. What you need to compute is expectation value. So already, even without wave function, we can do quantum mechanics. That's the key message that I want to convey in this lecture, okay? Any questions? Okay. Okay, so with that, maybe we can start a new section, which is about angular momentum. So remember, in the harmonic oscillator, the reason I want to talk about it again is to introduce this quantum bootstrap method, which is purely algebraic method. And now we are going to apply the same method to understand angular momentum. So everything is unified under quantum bootstrap. You only need to understand the operator algebra, and then that was sufficient to solve the eigenspectrons of these operators. Angular momentum is another important topic in quantum mechanics. It has to do with like particles rotating. So angular momentum in classical mechanics basically says that how fast or how much rotation are there stored in these particles or any system. Angular momentum of a quantum system is basically described in a very abstract way. It's described by three Hermitian operator, because we know that in three-dimensional space, when you do angular momentum is a vector that can point into any direction. So it has three components in a three-dimensional space. The three components of an angular momentum vector was called J1, J2, and J3. And then in quantum mechanics, every physical quantity will be promoted into a Hermitian operator. So angular momentum actually is a vector of operators. It's a three-component vector. Each component is an operator, and the operator is called J1 operator, J2 operator, J3 operator, correspond to the x, y, and z component of the angular momentum in the three-dimensional space. And these three operators has a commutation relation that is like that. And you may be very curious, why do I suddenly have this expression? But I think a better approach is to consider this as a definition of angular momentum, and we will justify this definition later. So in this commutation relation, it says that J8 and JB and ABC can be this 1, 2, 3. And then epsilon ABC is the Levi-Civita symbol, which is the sign of the ABC permutation. For example, epsilon 1, 2, 3 will be +1, and epsilon 3, 2, 1 will be -1. So this equation basically means that if you take a J1 and J2 here, and then their commutation relation of J1 and J2 will be plus I times J3, because this is a plus sign. But if you try to take the commutation relation of J2 and J1, then there will be minus I times J3. So it's always like that. When you put 1 and 2 here, 3 will appear there. And 1 and 3 there, 2 will appear there. But whether this is a plus IJC or minus IJC, this plus-minus sign, depending on whether ABC forms a cyclic permutation in the canonical order or the anti-canonical order, okay? So this is the meaning of this commutation relation. So this commutation relation, actually, there are it's three sets of relation, because you can do 1, 2, 3, 2, 3, 1, and then 3, 2, 3, 1, 2, right? There are three relations. And then these relations, so in this I also mentioned the indices are automatically contracted in this equation, which basically means this C gets summed over, actually, in this equation. But that's a minor point. Okay, and then equivalently, in terms of vector form, we can also write it in this way, because this is nothing but the definition of cross product. For example, if the third component of this vector, which corresponds to the cross product of these two, then it corresponds to J1 times J2 minus J2 times J1, which is exactly the commutation relation in the front. Okay, so that's just another way that people write it. So if you ever see that in the textbook, don't be panic. And then there's an example which try to justify why angular momentum looks like that. So there's one idea, which is angular momentum can arise from orbital motion of a particle. So if you have a point at the origin, and then there's a particle that is circulating surrounding the point, you can compute this angular momentum by taking x and p. X is the displacement of the particle from the origin, p is the momentum of the particle, then x cross p is the angular momentum of this particle with respect to that point that you choose, okay? So in quantum mechanics, both x and p are operators, so these are operators where actually there are three components. Every component is an operator. And then for this x and p operator, there's commutation relation. Because in any direction, x1 and p1, there's a non-trivial commutation relation. But x1 and p2, if they are x in one direction and p in the other direction, doesn't have any non-trivial commutation, because they are just motions in different directions, and then they are unrelated to each other. They are independent. So that's why the commutation relation looks like that. And then given that commutation relation, you can immediately verify that given this definition of angular momentum, orbital angular momentum in this way, the orbital angular momentum indeed satisfies the commutation relation as we proposed previously. If you want to see how to calculate that, you can look at exercise 13. I just show you how tedious that is. That's why I don't want to talk about it. But the idea is not difficult. You just need to substitute this definition of angular momentum in terms of position and momentum operator. That is for orbital angular momentum. And there's a lot of indices, but don't worry. Just stay with that. And then eventually you will end up with terms that simplifies to the right-hand side, okay? So that's orbital angular momentum. And there's another more abstract angular momentum called the spin. Spin is for example, electron carries spin 1/2. And then this spin 1/2 doesn't mean that the electron is really rotating. Actually, it's unclear to say whether it's rotating or not. It is just, you shouldn't think of electron as a sphere that is rotating, because electron really is like a point particle. And for a point, it's really difficult to define what does it mean by rotation, right? So spin angular momentum is an intrinsic angular momentum associated with some particles like electrons or quarks. So the spin angular momentum, then there's no x and p to describe that. It's immediately described in terms of these Pauli matrices, for example, for spin 1/2 qubit. And then previously, we have learned that we can combine these Pauli matrices. These are all the observables of a single qubit, but these are also the angular momentum observables of a spin. And then the spin is related to these Pauli observables by 1/2. And given that 1/2 factor, you can show that they indeed also satisfy this commutation relation. Because remember, for Pauli matrix, the commutation relation is like sigma A, sigma B commutation is I twice of I epsilon ABC sigma C, right? So now I have this 1/2 prefactor there that cancel that 2. So that's why it, again, gives you a spin or angular momentum commutation relation. So these are the two examples that people know about angular momentum. So given this example, I want to say this is the most general definition of angular momentum. So we will just stick to the most general definition, and whatever conclusion we result in the end will apply to both of the cases, orbital and spin angular momentum. For angular momentum, there's another operator. So it's just defining J1, J2, J3, but there's another operator which can be made out of J1, J2, J3, which is called the Kashmir operator of angular momentum, or sometimes called the square of angular momentum, which is J dot J, which is J square, which is J1 square plus J2 square plus J3 square. I should emphasize these are not numbers, you square them. These are all operators. When you square the operator, these operators, you should think of them as a big matrix, and then you are basically multiplying the matrix with itself. So this J square, again, it's the whole thing is an operator, and then it's like a matrix or an operator. So it's also a Hermitian operator. I forgot to mention that both J1, J2, and J3, they are all Hermitian operator because they all correspond to physical observables, and by definition, they must be Hermitian. And then if you start from the commutation relation between J1, J2, and J3, you can actually verify that the J square actually also has a commutation relation with any of the J's. And the commutation relation is simply trivial. So J square is an operator that commutes with all the J1, J2, and J3. That's actually the definition of Kashmir operator. Whenever we say operator is a Kashmir operator, that is an operator that commutes with all the components of this J. So if you can find an operator that commutes, that qualify as a Kashmir operator, and J square is the simplest one, the Kashmir operator, okay? Of course, J to the fourth is also a Kashmir operator because it also commutes with all the components of J's, right? But let's stick to J square. Okay, so the same trick is start playing. We want to play the similar trick again. Because previously, we need to define something like a number operator and also something like a creation annihilation operator. So here, for angular momentum, we also try to define something like that. So we try to first define something called raising and lowering operator. These operator, again, just like creation and annihilation operator, which is previously, it was made of x and p, x plus ip or x minus ip. But now, in this case, we can use J1 and J2, J1 plus or minus ij2 to define a raising and lowering operator. And this raising and lowering, this symbol, plus or minus, simply denotes whether you put a plus sign or minus sign here when you combine J1 and ij2. This is very similar or analogous to this Euler formula, where e to the I plus or minus I theta is like cosine theta plus I sine theta. You can really think J1 is something like cosine theta, right? Because it's like an x component of some vector, right? Sine theta is like a y component of a unit vector. So that's like J2, that y component. You can actually plus minus them together. I'm just saying that in terms of the form, these are very similar, and then you can actually use this to memorize this formula. What do I mean by raising and lowering? And then the raising and lowering operator are no longer Hermitian because J1 and J2, they are Hermitian operator. But with I, combining Hermitian operator together with an imaginary unit makes it no longer Hermitian. In fact, if you try to take the Hermitian conjugate of this J plus minus, it becomes J minus plus because the J1, J2 is invariant under Hermitian conjugate, but this I gets a minus sign, which flips the sign between plus and minus in this expression. So, so they are not Hermitian, but they are Hermitian conjugate to each other. Okay, and then this raising and lowering operator, again, has some algebraic relation, which if you try to multiply the raising and lowering operator together, you get an expression which is written fully in terms of J square, which is the Kashmir operator, and then J3, which is another component, the third component. And then I think this is just tedious evaluation. Just substitute the definition and then expand everything, and then you should be able to arrive at the result. Okay, you can take a look at by yourself. But these are the relation that we wish to define. So this relation, if you want to think about it, is very similar to the relation like A dagger A equals number operator, right? Previously, you should think of the right-hand side as some kind of number operator, and the left-hand side is made of creation, annihilation, or raising and lowering operator multiplied together. So this is this equation has that usage there. So that's one thing we want to derive. Another thing, remember, when we derive this annihilation creation operator, we pay a lot of attention on how to commute operators through the other operator. For example, if I have a number operator here, I have an annihilation operator here, I want to push the annihilation operator through the number operator, what should I do? So here, we want to derive the same thing. The same idea is if you have the raising and lowering operator, you want to push it through whatever operator on the other side, which includes both the Kashmir J square operator and then the J3 operator, the third component of angular momentum. So what you can show is that the first equation is actually trivial. You just push the raising and lowering operator there because the J square operator commute with every component of the angular momentum operator, including J1, J2, and J3. But this is just a linear combination of J1 and J2. So J1 and J2 both commute with J square. So the raising and lowering operator also commute with J square, meaning that you can exchange their order as you wish. But that's not the case with J3 because J1 and J2 both has non-trivial commutation relation with J3. So if you try to push the raising and lowering operator through J3, you will get a non-trivial result. And then the non-trivial result, again, looks very much like pushing an annihilation creation operator through the number operator. What happens is it's like a filter. Once you slide it through the operator, the filter itself doesn't change, but the operator gets plus or minus by 1. Basically, that's what happened to J3. So that's another algebraic relation that you can verify. So now, equation 106 and 107 are the fundamental relations that we need. And based on that, we can start the machinery of quantum bootstrap, I think. Yeah, so the idea is that, okay, here I also explained the physical meaning, but that's basically what I said. So this raising, so J3 corresponds to angular momentum in the z direction associated with rotation in the xy plane. So the raising and lowering operator really should be think as a spinning operator, which try to spin the system up along the z direction, meaning that spinning up the rotation in the xy plane. So if you observe J3 before applying raising and lowering operator, before or after. So this is like first spinning it up and then compute the angular momentum, or first compute the angular momentum and then spin up the system. Of course, because you spin up, you measure the angular momentum before or after spinning up the system, there will be a difference in the angular momentum, right, in the z direction. So that's why it gives rise to this plus minus 1. However, this J square commutes with all the J, which is a total angular momentum. So during this process, the total angular momentum is conserved in some sense. Yeah. So it's commuting and not getting changed by the raising and lowering operator, okay? And then if we consider any function of J square and J, So J square and J3, you can put it in any functions. For example, there's a function like that, which means it's a polynomial of all the J square operator and J3 operator. Then what you can do is now you can slide this through. If you slide this raising and lowering operator through, what happens is that this function, first of all, J doesn't get changed because of that commute. J3 gets modified by plus minus 1, which is based on that. But then if you slide this through there, you get a J minus plus and J plus minus meeting each other. But when they meet each other, it gives you an expression, which is this one in the front, which is exactly equation 106 above. Okay? So 108 is kind of like a combination of the previous two expressions, which allows us to eventually evaluate this very important final result, which again, as we see previously, we evaluate creation to the mth power and annihilation to the mth power, right? So here we are doing raising, for example, lowering to the L's power and raising to the L's power, or vice versa. So we want to understand what is the result of this of the expression on the left-hand side, because on the left-hand side is eventually where we want to use quantum bootstrap in the end. But then we need to express it to the right-hand side in terms of J square and J3. And then this is another recursive relation, because we already know the base case. When L equals 1, we know what's the answer. And when L is not equal to 1, you can always use this equation to lower the power by 1, and then eventually reach L equals 1. So eventually, based on the L equals 1 base case, which tells you how the raising and lowering operator product together into this expression, you can actually compute to all the power L. It basically goes like a complicated product like that. Okay, and that's unfortunately, it's complicated, but that's it. That's the most complicated thing there. So all we have done is basically we are turning an expression which is in terms of raising and lowering operator. Remember, raising and lowering operator only has to do with J1 and J2. But on the right-hand side, it only has to do with J square and J3. Basically, we are changing the expression that related to J1 and J2 to J square and J3. That's the role of this equation. With that, we can apply the quantum bootstrap idea. The problem set up is that J square and J3, because they commute, so they share the same set of eigenstates, which can be labeled by two independent quantum number J and little m, denoted like this. So that means I have a set of eigenstates because they are commuting, so they share the same set of eigenstates. And then that means if J square acting on the eigenstate gives you the same state with a scaling factor. And the scaling factor is some lambda depends on this eigenstate label, which is little j. And then J3 acting on the state also give you eigen. It's also eigen and then give you eigenvalue. So based on that, maybe I just quickly show you the answer, and then we'll do it again next time. So based on this idea, we can now apply a bootstrap idea, which means that there's an important relation called positivity constraint, which saying that for any eigenstates of J square and J3 labeled by this little j and little m, no matter what operator you apply on that, as long as you do this O dagger O and then sandwich between the same state, it must be greater or equal than 0, because this is like a cat state, this is like its dual bra state, and then the scalar product must be greater or equal than 0. So once you choose this, and then once you choose the operator to be the raising or lowering operator to the L's power, you can show that the raising and lowering operator, this guy must be evaluated to something greater or equal than 0. But this guy can be actually rewrite as a bunch of operators like that. And this bunch of operators now has very nice property, because this is a joint eigenstate of J square and J3. So J square acting on this state simply gives you the eigenvalue. J3 acting on this state gives you the eigenvalue lambda m. So you just need to replace all the J3 operator by lambda m, J square operator by lambda j. After this action, all these factors will go out, and then the state remain unchanged. So the state remain unchanged will basically scalar product with itself and becomes 1. So what you are left over is a bunch of products like that. So So this relation of positivity basically saying that this product must be greater or equal than 0 for any L. That's very similar to what we derived previously. And then that basically correspond to a set of inequalities. And I think we will try to solve them next time and show that indeed angular momentum is also quantized. And then there's a very special quantization rule for that. Okay, thank you for today.